We're going to begin our study of Taylor polynomials. And as you see, I've posed a question here, a couple of questions. How does your calculator calculate the sine of pi over 15? Do you think it has all those values stored inside? And of course, the answer is no. Your calculator uses something like Taylor polynomials, whatever that is. And of course, that's what we're discussing here. A Taylor polynomial is a polynomial that approximates a given function, for instance, like f of x equals sine of x. And in this particular case, a Taylor polynomial, and there's lots of them, represented as p subscript 5 of x for this sine function, x, and this polynomial is x minus 1/6 cubed plus 1 over 120 times x to the fifth. So this polynomial, p sub 5, is actually called a fifth order Taylor polynomial for the function f of x equals sine of x. And in this case, it approximates it very well as long as our x values are close to 0. When we get x values that are further away from 0, then it might not approximate it so well. In fact, you can see, and I apologize for this long blue line. I don't know what's happened there, but that keeps showing up now. But anyway, the black graph is y equals f of x equals sine of x. The blue graph is this p subscript 5. Okay, it's a polynomial. And notice, as long as we're using x values that are in here, it looks like almost an identical match, doesn't it? Now, when we get very far away from 0 for our x values, then the graphs don't look much alike. But for x is close to 0, they look very much alike, so it's a very good approximation. And so the question ends up being, well, why do we care about this? Well, we can evaluate polynomials quite easily. You only need to use addition, subtraction, multiplication, and division, as you well know, and a calculator can do that very well. It's very easy for a calculator to do that. It's very easy to program a calculator to do that. Now, having a calculator calculate the sine of pi over 15 is not so easy, but your calculator could use, this isn't what it uses exactly, but it could use this fifth order Taylor polynomial. This p subscript 5 is called a fifth order Taylor polynomial of f of x equals sine of x centered at 0. And it's important, we'll hear that terminology, and it's important to understand that this centered at 0 is the part that's telling us that this polynomial approximates f of x very well for x values that are near 0. If it was centered at pi over 3, then it would approximate values of x, the function for x values close to pi over 3, and so on. So for every one of these functions that we can create Taylor polynomials for, there's a first order, a second order, a third order, a fourth order, a fifth order, and further. And the larger the order, that has to do with the number of terms and the powers of x in the polynomial, then the larger that is, the better the approximation. And on the next page, we'll actually see that illustrated. So as you see here, here's the graph of f of x equals sine of x. As we move to the right, here's the first order polynomial. So a first order Taylor polynomial, and that has to do with the degree of the Taylor polynomial. In this case, it's just the polynomial is equal to x, which is of course just a straight line. And that doesn't really do too bad a job of approximating in this x values close to 0. But it's very far away from 0, it's not good at all. Now below, you'll see here's a third order Taylor polynomial. And it's x minus x cubed over 3 factorial, and we understand that 3 factorial is 3 times 2 times 1, so that's over 6 here. Now, this is a better approximation than p subscript 1, okay? You can see that it looks, the graph looks pretty good for more, the comparison, they match for more x values, more of the graphs match. Now, what we looked at a moment ago was p subscript 5, a fifth order polynomial. Notice we have a degree 5 here. And I wrote it a little differently. On the previous page, I had 1/6 times x cubed. Well, 3 factorial is 6. So this is the same as 1/6 times x cubed. And 5 factorial is the same as 120. So this is the same as 1/120 times x to the fifth. This is what we were looking at before. And notice as we increase the order of our polynomial, our Taylor polynomial, notice that the number of terms increase, but but in addition, though, we have matching terms. So the first two terms of this fifth order Taylor polynomial match the 3 terms over here. And I bet if we go higher, like to a 7th order polynomial, Taylor polynomial, which we see below, look, we have the first 3 terms match p sub 5 up here. Now, here's the 7th order Taylor polynomial. It's 7th degree. Notice that it's a better approximation. See, up here, it stops approximating it maybe to this far to the left. Well, that would be here, and notice it approximates it even better. And as you can see, when we go to the 9th order Taylor polynomial, again, the first 4 terms match over here, and we get even a better approximation. I mean, that looks like, you know, if we didn't see where they separated, that would look like one curve, wouldn't it? So it's a very good approximation here for x values that are what, between what is that, about negative 3.9, so almost negative 4 to positive 4. It's a very good approximation to the sine function. Wow. Well, I guess we need to know how here I've shown you what the Taylor polynomials are of different orders for y f of x equals sine of x, but I guess we need to decide, we need to know how we actually determine those Taylor polynomials. So we'll begin doing that on the next page. And so this is the definition of a Taylor polynomial. If we're given a function f of x, so we're given this function f of x, the nth order Taylor polynomial with its center at a. A while ago we had the center at 0. Okay, with the center at a is defined as follows. Okay, so p sub n for nth order is equal to the original function evaluated at a, which is the center of the Taylor polynomial, plus the term, the first derivative of the function f, evaluated at a, which is the center, times the binomial x subtract a. Remember, a is the center. That's something that we know. Plus, it's hard to read maybe, this is f double prime. Okay, so we take the second derivative of the function f that we're creating the Taylor polynomial for, take the second derivative of that function, evaluated at a, which is the center, divide that by 2 factorial, and then multiply that fraction with x minus a being the center again, squared. So notice what's going on here. Second derivative divided by 2 factorial, binomial squared. If you look at the next term, third derivative divided by 3 factorial, the binomial cubed. And we'll do this all the way until we get to n. So if n is 7, then we have a p sub 7, and out here we would have the, what does this represent? This is the nth derivative. You know, that's how we write it when we get above triple prime, don't we? When we get above third derivative. So this was the nth derivative evaluated at a over n factorial times the binomial raised to the power n. So we see some kind of system that's going on here. Now, of course, all the appropriate derivatives must be defined. They must be defined, okay? Otherwise, we couldn't find the derivatives and evaluate them, couldn't we? In one special case, sometimes we talk about the 0 order polynomial, Taylor polynomial. That would be p subscript 0. and p subscript 0 is just this first term, okay? P subscript 1 is the first two terms. But p subscript 0 then is just defined as f of a, which is only a point. And that's really, I think maybe our book asks us to do that, or homework asks us to do that, but that's really not very useful. Now, it's important to recognize how these build, just as to point out. Here's the definition of the nth order Taylor polynomial all the way out to where we're taking the nth derivative and we have a power of n and we're dividing by n factorial. But notice, of course, if we're looking at p sub 1, then we're looking at the level of the first derivative and a power of 1. If we're looking at p sub 3, well, when we add up all the values until we get to a value of 3, so that's the third derivative, 3 factorial, and a power of 3 on the binomial. So we see that pattern, and that's what we'll be developing and using as we go through problems we're actually doing this. Okay, so another note here, if the center is at 0, if the center is 0, that is the a value is 0 that we're given at the very beginning, we sometimes use a special name for this this nth order Taylor polynomial. When the center is 0, sometimes it's called an nth order Maclaurin polynomial. And of course, if it's an nth order Maclaurin polynomial, that means the a value is 0. So we have a 0 in this position. We're evaluating the function at 0, the original function, not the polynomial. We're evaluating the first derivative at 0. And then, of course, we have, if we look above, x minus a. Well, since a is 0, that's just an x. And, of course, we're evaluating here a is 0. Well, in this case, if a is 0, we have x minus 0, or just x squared. And so we don't see that extra part of that polynomial. It looks like to be a little simpler expression. So this is when our center is at 0. One time also we'll call it a Maclaurin polynomial. Well, let's look at an example. So here we're asked to find the third, fourth, and fifth order Taylor polynomials for f of x equals sine of x, centered at a equals 0. Actually, it probably would just say centered at 0. So let's keep in mind what this is asking us to do. We need to calculate the appropriate components to build the following three polynomials, as I've stated here. So the third order Taylor polynomial is stated in this way, p subscript 3. And remember, it's f of a as the first term, and if a is 0, then it's f of 0, plus the first derivative evaluated at a times x to the first power. It's times x minus a, all to the first power, but since a is 0, that's just x to the first power, plus the second derivative evaluated at 0. We're doing this till we get to the third derivative, aren't we? Over 2 factorial times x minus a, of course a is 0, so x minus a squared, or just x squared, and then likewise for our third derivative. Now, so when we look at the fourth order Taylor polynomial, then of course we'll have up to the x cubes, and we're adding the x to the fourth. So that's the fourth derivative evaluated at a, which is 0, over 4 factorial times x minus a to the fourth power. In this case, that's just x to the fourth. And then likewise, for the fifth order Taylor polynomial, we'll have the first 4 derivatives, and then we're adding the fifth derivative evaluated at a, and of course over 5 factorial times x to the fifth, x minus 0 to the fifth power. So that's what we've got to work on. So the way I do this, at least, is I start by finding, I need up to 5 derivatives here, don't I? So I start finding the derivatives. And so that's what I'm going to do here. We start out with a function f of x. I apologize for that blue line again. F of x, which is equal to the sine of x. So what's f prime of x? Oh, it's the derivative of sine of x is cosine x. And what is f double prime of x? Well, that's the derivative of cosine x, which is negative sine x. Okay. What's the third derivative? That is the derivative of negative sine x is negative cosine x. The fourth derivative, of course, is the derivative of negative cosine x. And of course, the derivative of negative cosine x is the negative of the derivative. Since the derivative of cosine x is negative sine x, we have negative of negative sine x, which is positive sine x. At this level, I'm sure you can follow along and think this through pretty quickly on your own. And of course, the fifth derivative would be the derivative of the fourth, and the derivative of sine of x is cosine x, so the fifth derivative is cosine x. Now, here's what I do next. I go back, and now what are we needing to do? We're needing to evaluate each of these as 0. So I just go back and say, okay, well then, if f of x is sine of x, what's f of 0? It's the sine of 0. And the sine of 0 is 0. So now I want to know f prime of 0. Well, f prime of x is cosine x, so f prime of 0, of course, is cosine of 0, and cosine of 0 is 1. Okay, I guess I should have put this up a little earlier. What we're really, what are we really doing here? We're trying to calculate. I just used the lower value, and remember what it is. It's from above. This is just from above. This is the third order, and so we need all of these pieces of information. We'll probably use this a little lower as well, but we need the f of 0, we need f prime of 0, we need f double prime of 0, we need f triple prime of 0, and that's actually what we're working on right now, isn't it? So let's get this out of the way, at least for now. Okay, so now we're needing f double prime of 0, just as we see up here. And of course, that's negative sine of 0. And since sine of 0 is 0, then we get 0 again. And now we need f triple prime of 0. And so we just evaluate that at 0. So we have negative cosine of 0. And since cosine of 0 is 1, we get a negative 1. Notice we're getting some derivatives that are actually 0 here. And likewise for the fourth derivative at 0 is just the sine of 0, which is 0. And the fifth derivative at 0 is cosine of 0, which is 1. Now, that's going to play out for us here. Remember what it is we're trying to do, okay? It's going to play out these derivatives being, some of these derivatives being 0. Maybe I should get that out of the way. I apologize for running all over the place here, because we're going to need these pieces right here when we start filling in. And I'm going to go up and down a bit, but now we're building the polynomials. So let's keep in mind what's going on here. Piece of 3, the third degree polynomial, Taylor polynomial for f of x equals sine of x is built in this way. And we now, of course, have f of 0, which is 0. And we have f prime of 0. It's hard to see all the way up here. F prime of 0 is 1. And so I've replaced f prime of 0 with 1. Now we also have, and times x. So here's f prime of 0, here's x from above. Then we've got to worry about this term. Well, this term is f double prime of 0 over 2 factorial times x squared. And if you look above, f double prime of 0 is 0. So this part of the fraction becomes 0, and so that term doesn't even show up, does it? We have a 0 there. And of course, f double prime of 0, f triple prime of 0 was a negative 1, and so that's why we're replacing this with a negative 1. And so we're just cleaning up that a little bit, okay? Cleaning that up a bit. And of course, we don't have this term. That's just 0. We don't have this first term, so we replace 1x with just an x. And then we end up with minus, see, because it's negative 1, minus just x cubed over 3 factorial. And of course, 3 factorial is 6. And so this could be simplified to x minus x cubed over 6. And so this is the example. There's y equals sine of x. And here's the polynomial, the third order Taylor polynomial centered at 0 we just found. That's what we've actually done. Now we were asked to find the fourth order Taylor polynomial, so that means that's what we're calculating. And so now we're just filling in the f of 0, the f prime of 0, f double prime of 0, and so on from the work that we used above, where we calculated. So f of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, f triple prime of 0 is negative 1, and the fourth derivative evaluated at 0 is 0. And so in this case, and that's the reason I'm doing this, in this case, we actually end up with the same result we had a while ago, because for the fourth derivative, we got a 0. And so this isn't any different. And if you noticed earlier on, I just showed you odd orders. I showed you p sub 3, p sub 5, p sub 7, p sub 9, because this happens for all of the even orders. And then, of course, for the fifth order, which we already had above, we're filling in the terms here. So all we need to do is fill in the pieces, if you will. F of 0 is 0, f prime of 0 is 1, and so on all the way out here. And if you look way up above, the fifth derivative at 0 is 1. So all of the rest looks the same. And then we just clean that up a little bit. That's really all we're doing. We don't need to put this 0 on 1x, we say x. Of course, this middle term is gone, and so this becomes 1 minus x cubed over 3 factorial. This term is gone, and so this becomes plus x to the fifth over 5 factorial, which could be written in terms of the factorials being evaluated. 5 factorial is 120. 5 times 4 times 3 times 2 times 1. And of course, here's the sine function in black, and here's the p sub 5, the fifth order Taylor polynomial centered at 0 for the function. It's a good illustration of what's going on. Let's look at an example next that has a center other than 0. In fact, we'll look at the same function, actually, f of x equals sine of x, but the Taylor polynomials now are going to be centered at something other than 0. And just for illustrations, we won't go as high as the fifth order here, but find only the third order Taylor polynomial, I should say, my bad, for f of x. Oh, I changed it. F of x equal cosine of x, centered at a equal pi over 3 rather than at 0. And of course, in the future, it will just say find the third order Taylor polynomial for f of x equal cosine x, centered at pi over 3. Okay, I'm just trying to illustrate the difference. So we need to calculate the appropriate components, and so I'm just reminding you, if it's centered at a, then it looks like p sub 3 looks like f of a plus f prime of a times x minus a to the first plus f double prime of a over 2 factorial times x minus a to the second, and so on for the third derivative. Okay, so that's what so what components do we need? Well, we need to know f prime, f double prime, and f triple prime for this function f of x equal cosine of x. And then we need to evaluate each of those at our a value, which is pi over 3. So we begin doing that, okay? So I've just rewritten it then, because a is pi over 3, then we need f of pi over 3 plus f prime of pi over 3 times x minus pi over 3 rather than x minus a, and likewise all the way through here. That's what it will look like. And so we won't expand. You know, we're going to leave x minus pi over 3 squared alone when we create this polynomial. But we have some work to do. So we'll start by finding the first through third derivatives and evaluating each of them at a equal pi over 3. So here's what I've done. I approached this one a little differently. F of x is equal to cosine of x, and we need f of a. We need f of pi over 3, so we need to calculate the cosine of pi over 3. And the cosine of pi over 3 is 1/2. I hope that you can do that pretty rapidly, even without a calculator. And then we need f prime of x. Well, we look up here, f of x is cosine of x, so f prime of x is negative sine x. So now we're evaluating f prime at pi over 3, so we have negative sine of pi over 3. Sine of pi over 3 is the square root of 3 over 2, so f prime of pi over 3 is negative of square root of 3 over 2. And likewise now for the second derivative. Well, for the second derivative, we take the derivative of the first. And the derivative of sine of x is just cosine x, so we have negative of cosine x, don't we? Now we evaluate that at pi over 3, so we have negative cosine of pi over 3, which of course is negative 1/2. And finally, we use the third derivative, And of course, for the third derivative, we're looking at the derivative negative cosine x, which ends up being positive sine x. And so we evaluate the third derivative of pi over 3, which is sine of pi over 3, and we get square root of 3 over 2. By the way, in the last example, when we were centered at 0, because we had the sine of 0 is 0, we saw that some of the terms went out. See, here, if we looked at the fourth derivative, we would end up with the fourth derivative evaluated at pi over 3 would be 1/2 again. So we're not getting any of these terms to disappear like we did in the last example when we were centered at 0. Centered at 0 doesn't mean you'll have terms disappear. It just was specific to that particular problem. So now we build this polynomial with the information we have above, and you can rewind and go through. I don't want to be jumping up and down so that you can't see what we're doing, but we're just replacing each of these with the parts that we've calculated. So we found f of pi over 3 to be 1/2. We had f prime of pi over 3 to be negative square root of 3 over 2, and so we have x minus pi over 3 to the first power. And then we found f prime of pi over f double prime of pi over 3 to be negative 1/2, and it's real hard to see, but there's a division bar right there, negative 1/2 over the 2 factorial that's there, and then we have the binomial squared. And f triple prime of pi over 3, it's hard to see that division bar, I notice, but that was square root of 3 over 2, and that's what we have here, square root of 3 over 2, and it was positive over 3 factorial. So now we just go back and clean this up. That's really all we're doing here. Not much to do in these first two terms, but this negative 1/2, well, that negative we can write as a subtraction, and that would be 1 over 2 times 2 factorial down here. And of course, in this term, this fraction, we can write that as the square root of 3 over 2 times 3 factorial. So the 2 times 3 factorial from that denominator is showing up here. Okay. And well, I guess there we go. And obviously we clean this up. 2 factorial is 2, so this is really a 1/4. And 3 factorial is 6, so this is really a 12 down here, square root of 3 over 12. We could clean it up so that it didn't have those factorials in it, and that would be easy for you to do. Now, here's the case in this instance. Remember, we were centered at what? Pi over 3? Centered at pi over 3. So, when we're close to 0, this isn't particularly a good approximation. But pi over 3 is just about 1, isn't it? Pi is about 3.14 over 3, so that's about 1. So we're centered at an x value of 1 here. And so when we're looking at the graph around this point on the graph, yeah, that's a pretty good approximation on either side of that x value of 1, isn't it? We get very far away from it, then the approximation isn't very good. But right here around where x is 1 is a pretty good approximation. Now I have some other examples, but they're not listed with this particular discussion, but they are listed in your homework and in the lecture part, some more advanced examples that probably are a good idea to look at separately. But that's all for what we've got in this lecture. In fact, what I think I'll do here, we're at the end of this, my bad, I've kind of jumped around, and here's that graph. Okay, I think what I'm going to do is just go forward and show you what other things there are to look at in the other videos, and they're in a little different format, as a matter of fact. You have to play those movies a little differently, but you ought to be able to do that. That shouldn't be trouble. So one of the problems I'm going to do for you is finding the Maclaurin series. Remember, Maclaurin polynomial, Maclaurin polynomial means that the center is 0. And so we're going to find the Taylor polynomials, if you will, of order 0, 1, 2, 3, and 4 for this function f of x equal e to the x when we're centered at 0. Another one that I want to, and you kind of see a result, is find the fourth order Maclaurin polynomial for this function, f of x equal e to the negative x squared over 2. Remember that we're talking about a fourth order Taylor polynomial where the center is 0. And here, of course, we see the polynomial is in blue and the function f is in black here. And the reason I'm doing this one is because it becomes a little more of a job because finding the derivatives is more difficult. And so it's something that you should consider. And I think the last one I want to do, and this is an interesting problem, is to talk about approximating a definite integral, one in which we have no way of actually calculating the indefinite integral. See, we don't have a way to calculate the integral of e to the power negative x squared over 2. We just don't have a way of doing that. And that is another way these things come in handy, is that we can use these polynomials to approximate an integral that we wouldn't otherwise be able to do. So that would be an interesting video to look at, I think. Oh, yes, I forgot about this. This is something else that's very interesting and that you'll have to do in your homework. Use a Taylor polynomial of order 3 to approximate the value of the natural log of 1.05. Remember, we've talked about this already. This is kind of another good look at, well, what does your calculator actually do? Well, it doesn't have a listing of natural log values in it. There's no way it could hold all the possibilities. So what it does is it replaces the natural log function with an appropriate Taylor polynomial, and then it evaluates that Taylor polynomial for the number that you're interested in. And because it has an easy way to generate polynomials, that's not a problem. So this is another good problem that you ought to be looking at, which is in the extra videos. Okay, well, that's all that I've got.